Alright, so here on page 15 we're going to talk about the final way that we can calculate enthalpy. And this isn't actually really a completely new way, it's really a different way experimentally that we can get to that enthalpy value. And calorimetry, as the name implies, is about measuring heat, and measuring heat flow specifically. And this is generally done using what's called a calorimeter. And there's actually a picture of one of these on the top left. They can get really complicated, but at the basic level, it's a container generally filled with water or a substance that absorbs heat at a predictable rate that you can immerse some kind of chemical system in or object in order to be able to observe how the calorimeter and its water has temperature changing in order to infer some information about the heat that is coming from that object or going to that object, that system that we immerse in it. So we basically use the energy change of a known system, which is technically surrounding the system we're actually interested in, to get us either better, more precise measurements, or measurements where we wouldn't otherwise be able to take them, because we can't always stick a thermometer into a reaction and get a good measurement, especially not without affecting their results. So one of the key ideas with calorimetry is that the amount of heat being lost by that substance or system is equal to the amount of heat being gained. Now in physics, we probably put a negative sign on our equation saying that they're inverse, that the heat is lost is equal to the negative of the heat being gained. But we've already kind of talked about those negative signs and how the AP chemistry exam isn't as picky about where they come from and where they go. And a lot of these problems I think are actually easier to work out if we don't set up an equation fully first, that we solve for the values that we need and plug them in kind of in the wild so that we don't have to be stuck and kind of confined to an equation. But when it comes down to it, we're going to be using the temperature change of our calorimeter, so that's going to involve our MC delta T equation every single time, in order to get information about some other system that's changing heat, whether that is another system changing temperature, another MC delta T, a reaction producing heat that we can measure with that MC delta T, or even a phase change, something melting, freezing, boiling. So anything that we can already use to solve for Q, we could plug in on the other side of this equation technically and be able to calculate our unknown value, whatever it is we need to know, based off of the measurable change that we observe in our calorimeter system. So there's a couple different problems we're going to work down below. But a key idea with all of them is this idea of thermal equilibrium, meaning that when two substances are in contact with each other and exchanging heat, that they will keep exchanging heat until they become the same temperature. So if we have a hot object and a cold object and they're touching, then the hot object is going to get colder, the cold object is going to get warmer, and it's going to keep going until they get to be the same temperature. Once they're the same temperature, then they're going to stop changing temperature. So, in all of these problems that talk about two objects being in contact and changing temperature, you'll probably have two different initial temperatures, but you're only going to be given one final temperature, because you need to make sure you remember that final temperature is the final temperature of both objects, because they were in contact with each other. The last thing that I want to make sure to mention before we move on is to remind you something we've talked about occasionally. The density of water is 1 gram per milliliter. Like I said, water is used oftentimes in our calorimeters, and they could tell you the mass, which is generally what we need for these equations, is m's, but they might give you a volume of water being used. And so it's actually equivalent. The milliliters that you're given for the volume is the same number, the same value of how many grams of water you have there. So that will be necessary in at least one of our problems down below. So let's take a look at that first problem. This tells us a coffee cup calorimeter, which is really just a simple calorimeter made from a couple of insulated styrofoam cups. So this isn't a high value item, but it actually works pretty well. And evidently this coffee cup calorimeter contains 150 grams of water at a certain temperature, and then we put a 110 gram block of molybdenum that was heated to 100 degrees Celsius and placed into that water in the calorimeter. The contents of the calorimeter come to a temperature of 28 degrees Celsius. What is the heat capacity in kilojoules per gram of molybdenum? So we do have two things changing temperature here. So you might be thinking, oh, we're using an MC delta T to figure out an MC delta T. The only issue is that the heat capacity we're looking for isn't looking for the same units as the heat capacities that we already have. So we don't want to just use two MC delta T equations because we're not going to get it in the units they want. So this is one of those situations where I'd really just recommend your default is solve for each of these units separately. Let's use our Q equals MC delta T to solve for our kilojoules of energy, and then we can take these grams of our grams of the molybdenum. We're going to need the grams of H2O here in a minute for our MC delta T. We can take the grams of molybdenum and take the amount of energy that molybdenum released, divide it by the grams, and get this answer. So, in order to find the kilojoules part of this, then we are going to need to use the information about water, which is why H2O is the mass that I highlighted. We don't care about that 110 grams yet, because even if we did want to use that 110 grams, that's our M, and we could look at our delta T of our molybdenum, but then we would end up with a C value that's not in the right units. So we need to use the information from the water to find information about molybdenum. So we're going to use MC delta T, and our temperature change of the water is going to be when it changes from 28 to 24.6, which is 3.4 degrees. If we plug in the mass of water and that specific heat of water along with that temperature change, then we get 2,133 joules of energy that was absorbed by the water, which is 2.13384 kilojoules, which rounded to 2 sig figs because my temperature change is 2 sig figs, is 2.1 kilojoules. So I've got the kilojoules part of my answer now, and now it's time for grams. Well, we already had grams, so let's put those together. When we ask for kilojoules per gram, that means kilojoules divided by grams. So we're just going to take that 2.1 divided by 110, and that's going to equal 0.019 kilojoules per gram, which is our final answer. So notice how it's talking about and concerned about molybdenum completely, but we used information about water in order to get some information about the heat in this molybdenum, because all of that heat that went into the water to heat up the water came from the molybdenum. So hopefully that's not too bad. It's just kind of a more complicated Q equals MC delta T problem where we're using information about multiple substances to come up with an answer about this energy change. Now, in our second example, this is truly where we're going to be calculating enthalpy. We're going to be determining the heat of dissolution, so the delta H for the reaction where ammonium nitrate is dissolving. And this is once again very picky and particular about units. And so here, once again, we're going to just use our Q equals MC delta T equation and solve for the kilojoules, and we can find moles real easily. We got 4 grams of moles given to us. Ammonium nitrate, I probably could have or should have given you that formula, because that is kind of a double polyatomic there, NH4NO3, but we can add up that mass real quick, turn those grams into moles. That would probably be where I started, because I know I need moles if I need kilojoules per mole as my answer. And now we're just going to go through and do the same thing we did before and pull out information about the temperature change the water went through to get information about the heat that was produced or absorbed by this reaction. So Q equals MC delta T. Here it mentions that we have 100 milliliters of water, but once again, water is 1 gram per milliliter, which means that that is 100 grams of water. And then our temperature change here from 22.5 to 19.3 means that we change temperature by 3.2 degrees. And if we plug all of that in together, then we get 1.3388 kilojoules. Once again, it's going to come out in joules because our standard and heat capacity has just normal joules in it. But if we want kilojoules, we move that decimal 3 times to the left, and we've got our kilojoules. And now we just need to divide the kilojoules by our moles. 1.3 divided by 0.05 gets us 26 kilojoules per mole. Once again, just kind of a fancy Q equals MC delta T with an extra couple of steps that we use here, and with the understanding that we're using information about water to find information about another system, this time an actual enthalpy value for this reaction. Okay, now finally, get rid of that ammonium nitrate. We have this one particular type of problem, and I gave you 2 types of problems here. Sorry, 2 versions of this problem here, because this is a very common situation where this is just going to be trying, we've got 2 objects in contact changing temperature, a metal and water, and one starts hot, water starts cold, put them together, we get to the final temperature, and we can use that information about how much metal we put into the water and how much it all changed temperature by to actually identify that metal. And we can do this in a very precise way with other tests to actually figure out the proportion of each of these metals. Pardon that, sorry for the interruption. So really what we're doing here is there's 2 things changing temperature, and a metal and our water. And I have our kind of QM equation here and QW, and it's just very specific with each. And we're just going to set those equal to each other and plug in the values we know. This time we can solve for our specific heat C because we're identifying a substance from this table where we're already using one of those same C's. So if I put in my C of water with these particular units, this C that I get for the metal is going to come out with those same units, which is good here. That's what we want because we're going to use the same units from this same table. So here it's just about plugging in our numbers really carefully. I'm not mixing up the information about the metal and the water. And so looking at our temperature change of our metal, we said that we started at 90 degrees and our final temperature of both our metal and our water was 23.4, so that's a temperature change of 66.6. And our water went from 22 degrees to 23.4. That's a temperature change of 1.4 degrees. Now if we plug in the mass of our metal is 55, the temperature change of our metal is 66. We don't know the C of the metal, that's what we're solving for. Mass of water was 250. C of water we know, it's given in the table. And our temperature change of water. We can plug all that in, and you can do this in one step or multiple steps. You could multiply these numbers together, kind of multiply those numbers together to get a simplified equation, but however many steps you go through here, you should end up with a CM, C specific heat of our metal, ending up being 0.39978, which we would round down to 2 sig figs, which would be 0.40. And once again, those units would match the units in our table, joules per gram degree Celsius. And while nothing is exactly 0.40, the closest option in the table is copper at 0.39. So that is our best guess based off of these calculations, the best we can do. And yeah, with our rounding, we did round that up just that little bit, so that's a pretty plausible guess here with our measurements. If we want to get more precise, we could get a better thermometer, a better mass, or both. So hopefully that's not too bad, because like I said, we've got another problem just like it here. And we actually need a real quick fix. That final temperature there, instead of 43.9, should be 45.9. That's going to actually make a pretty significant difference in this problem. So go ahead and fix that there before we begin. We're going to go through the same process here as we did in the last one. We've got two things changing temperature, our metal and our water. And so we're going to find how much each of them separately is changing temperature by, just doing that temperature calculation from where they started minus where they ended. And then if we plug all of those numbers in, being very careful to keep all the metal numbers together, all the water numbers together, simplify and or solve, then our C of our metal is going to be something like 0.90305, which we would round down to 2 sig figs. And this does end up matching exactly with aluminum. So, calorimetry is all about taking measurements of one object or system to learn more information about the temperature change of another object or system. We're going to use this in our lab, so hopefully it's not too bad, and I'll help you through the bits that are a little bit special and different for the lab. But that's it for these notes.